There we go. All right. Hey, Charlie, Daniel, how are you guys doing today? We're talking some chemistry. Module 10, gases. So let's get right into it, and I won't waste too much of your time here. We are going to share my screen, get into the PowerPoint. Now, this is a heavy chapter, heavy module, a lot of formulas, and there's four experiments. Three of them are pretty straightforward, pretty simple, that you probably have a good portion of the materials for some of these experiments at home. So I want you to look at experiments 10.1, 10.2, 10.3. If you have all the materials for any of those labs at home this week, I want you to do one of those for me and write it up. That would be perfect. That is part of your, no, let's make it extra credit. Let's make it extra credit. Charlie, you're on the road, so let's not get too crazy here. So extra credit if you do experiment 10.1, 10.2, or 10.3. 10.4, that one requires a little bit more material, so we may do that one in class next week, but I need to look ahead to the module 11 experiments before I guarantee that one. So chapter 10, gases. Little chemistry humor here. Laughing gas. Laughing gas is not helium. Helium, of course, is nitric oxide, but you get the joke, I hope. I hope you do. Now, like I said, this chapter, when we're talking about gases, there's a lot of math involved, a lot of relatively simple algebra, but it's pretty cool chemically what we can do or predict with gases. And this is you're going to be your simplest equation right here, pressure. Pressure is the force per unit area of an object. So therefore, the formula pressure equals force divided by area, force over a given area, in other words, is pretty simple, pretty straightforward, and makes perfect sense. So the pressure is the force exerted on a particular area of a gas. We label that as Pascal, PA, and we measure it in newtons per square meter. Now, when we're talking about pascals or pressure, from an environmental standpoint, the thing that comes to mind is atmospheric pressure, the air all around us. Atmospheric pressure is just that, the pressure that the atmosphere exerts on everything, including you. Right now, the air is exerting a pressure on you, even though you don't realize it, because your body, your skin, and your body are exerting an equal and opposite pressure to balance that atmospheric pressure out. The typical average atmospheric pressure is 14.7 pounds per square inch, or 101.3 kilopascals, which was equal, obviously, 101,325 pascals. So the atmosphere can be measured in a number of ways. Atmospheres, pounds per square inch, kilopascals, or torr, millimeters, and mercury. When you see weather, for example, on the Weather Channel, usually you'll see it measured in millimeters of mercury. That's a barometric pressure. So using a barometer, 760 millimeters of mercury, equal to torr, equal to 101.3 kilopascals, or 1 atmosphere, which again is 14.7 pounds per square inch. Now, we can take that information that we know and we can put that into more chemical or physical laws. And one of them is Boyle's law. Boyle's law says that at a constant temperature, so when the temperature does not change, pressure and volume are inversely proportional to one another. Pressure and volume are inversely proportional to one another. So if we decrease the volume, we are going to increase the pressure. You see the schematic to the lower right. If we take a specific volume of a gas, and if the temperature doesn't change, if I decrease the volume, I'm going to increase the pressure in an inversely proportional way. Therefore, Boyle's law says pressure and times volume of a gas is equal to the pressure times the volume of that same gas if we change the volume or the pressure in those circumstances. So here, P1 would be down here on pressure of the first scenario, 100 millimeters of mercury. Our volume is 1 liter. If I decrease the volume to half a liter, I'm going to inversely increase the pressure. That's going to be the result, is a doubling of the pressure, so that we get the same number, right? 1 times 100 equals 100. That's the pressure times the volume of circumstance 1. And 200 times 0.5 equals 100. And so P1 times V1 equals P2 times V2. Now, Charles' law says this: at a constant pressure, the temperature and the volume of a gas are directly proportional to one another. So here we're keeping the pressure at a constant, and in that case, the temperature and volume are directly proportional. So V1 over T1, volume of the first circumstance, over the temperature of the first circumstance, is going to equal the volume of the second circumstance over the temperature. So if we see this chart to the side here, as I increase the temperature, my volume is going to go up proportionally. If I move to the right on the graph with the temperature, the volume is going to go up in a proportional way. That's equation 10.3 in your book. Now, equation 10.4 is Kelvin scale. Kelvin is a scientific unit of measuring temperature, and we will use Kelvin in this class from this point forward. Kelvin equals degrees centigrade or degrees Celsius plus 273.15. So 0 Kelvin, therefore, is negative 273.15 Celsius. Got that? I know you do. Now, we can take both of those, Boyle's and Charles' laws, and we can combine them into what we call the combined gas law. And that is P1V1 over T1 equals P2V2 over T2. When you use any equation in this module, you must convert to Kelvin is the important thing. Check out example 10.2 in your textbook. 10.2 is where? 10.2 is on page 298. 298 is where that example is, and you'll find equation 10.5, the combined gas law there. In fact, now that you know the combined gas law, quite frankly, you don't really need to know Boyle's and Charles' law, but it's good to know which is which. That would probably be the more important thing. I wouldn't necessarily, you don't need to know how to apply Boyle's and Charles' law because they're incorporated into the combined gas law. Now, there is such a thing called an ideal gas. An ideal gas is a gas that behaves in a predictable and consistent manner. Ideal gases have the following properties. They are made of very tiny molecules. They demonstrate rapid motion in straight line and in random directions. Gas molecules have no attraction to one another. They undergo elastic collisions, and the average kinetic energy of a gas molecule is proportional to the Kelvin temperature. So kinetic energy directly proportional to temperature, Ke directly proportional to the temperature. Why is that important? Because there is such a thing where molecules no longer move, and that's 0 degrees Kelvin. So if the colder it is, the less these molecules are going to move. Now, At standard temperature and pressure, that's 273 degrees Kelvin, or 0 degrees Celsius, or what would that be, like 32 degrees Fahrenheit, right? At standard pressure and temperature, that's when we're going to measure our ideal gases. So don't worry about 0 degrees Kelvin, we're never going to be there. We're going to consider everything to be at standard temperature and pressure, STP. But there is, there's another law, and therefore another equation. That's this ideal gases. PV equals nRT. What does that mean? Pressure times volume equals N, the number of moles of this substance we're measuring in a gas. So again, PV equals nRT only applies to gases. R is the ideal gas constant, 0.0821. And temperature is just that, temperature in Kelvin. Always remember to convert to Kelvin in temperature. I'm going to move my my picture here. I don't know if it makes a difference to you or not, but so you can see the whole of the formula. Pressure times volume equals the number of moles times the gas constant. Again, that's 0.0821 liters times atmospheres over moles times Kelvin, times the temperature. That's a law along with the combined gas law and the equation 10.1, which was the pressure equals force times area. Those three equations are probably the three most important ones you want to know right now for testing purposes. Okay, let's move on to stoichiometry, gases and stoichiometry. Avogadro's law says equal volumes of all gases at the same temperature and pressure have the same number of molecules or atoms. So get that, that is an interesting concept and an important one. Equal volumes of all gases at the same temperature and pressure have the same number of molecules. Well, if they have the same number of molecules, that gives us a clue there. So we can say that N, the number of moles in our ideal gas law equation, the number of moles N equals PV over RT. Well, R is a constant, 0.0821. We're going to know the pressure and the volume, and we can figure out that temperature too. So when all substances of interest are gases, as long as pressure and temperature are the same, the equation gives you the relationship between the volume of those gases. And so what are we talking about there? Dalton's law of partial pressure. Dalton's law says when two or more ideal gases are mixed together, the total pressure of the mixture is equal to the sum of the pressures of each individual gas. Equation 10.7. You'll want to know that one for your test. So P total equals PA plus PB plus PC, etc. So in the schematic here, if my pressure of oxygen is 20.9, nitrogen 78.1, argon, water, and carbon dioxide, I can add up the partial pressures of all of those because it's going to give me the complete pressure of air, 101.3 kilopascals. That's the standard air pressure, right? At what? Surface level of the ocean, that's called whatever. Can't think of it. I have a little bit of a brain freeze there. It'll come back to me. Dalton's law alternative, our mole fraction. So XA, so if we have a component of a mixture of air, right? The number of moles of a component of air, of a mixture is divided by the total number of moles in the mixture. So XA can also therefore equal PA divided by P total. Partial pressure of gas, total pressure of gas. Vapor pressure is our next topic. Vapor pressure is the pressure exerted by the vapor in gas phase that sits on top of any liquid. So perfect example, my glass of water here. At the top of my glass is air the bottom of my glass is water, right? Well, at that cusp between the water and the air above it, there is a pressure, and that pressure is exerted by the vapor that sits on top of my water. So it's not the air, it is 100% water vapor, and that is the vapor. That vapor is a pressure that is responding to the pressure of the atmosphere, the atmospheric pressure. There we go. That's what I was thinking of at sea level. And now the boiling point is the temperature at which that vapor pressure of a liquid is equal to the atmospheric pressure. So the boiling point is when the vapor pressure is equal to the atmospheric pressure, which means this right now, right? The vapor pressure of my water in this glass is less than the pressure of the air. If it wasn't, my water would be boiling, right? So either the pressure of the air, the atmosphere would have to decrease, or the pressure of my water would have to increase. If I heated up my water, we're going to get to a point where the vapor pressure of my water is going to be equal to the atmospheric pressure, and then my water is going to begin to boil. And that's the boiling point, the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. So here we can see the vapor pressure of water. Notice on the x-axis along the bottom here is temperature in degrees Celsius, 0 to 100. And up is pressure in torr, or we could also measure that obviously in millimeters of mercury, because torr and millimeters of mercury are the same. So notice here, 760 torr, that's going to be where this blue dot is. 100 degrees Celsius is the boiling point of water. So the vapor pressure of water increases with increased temperature until it gets to the boiling point. And at that point, well, water boils. But until that point, it does not. All right, some problems that you should do before you take your test. On pages 302 to 316, examples 10.8 and experiment 10.4. That one we're going to do in class again when we return. So gentlemen, I went through that extremely fast. Feel free to watch this a couple times or pause it. But know those formulas, especially equations 10.1, 10.5, the ideal gas law 10.6, and also know partial pressure 10.7. Those are the important ones. So there we go. We're back. So therefore, get those done. Do your practice problems and get Module 10 test done as you can. Here, if you can't get it done because you're on vacation, Charlie, don't sweat it, but just get it into me as soon as you can. We're going to pick up Module 11 next week, the 19th, and we're going to keep rolling through this chemistry, man. It just keeps getting better. A lot of fun. Talk to you guys soon. Bye-bye.